In this video, we will talk about derivatives and definite integrals of complex valued functions, w, of real variables, t. So first, we're going to look at what a complex valued function of a real variable looks like. So here we have w of t. It's a complex function. You can see it has a real portion and an imaginary portion. And t is a real variable. So t is a real number. So this is what we mean by complex valued function of a real variable. First, we will look at the derivative of complex valued functions of real variables. So if we have a complex valued function w, which is equal to u of t plus I v of t, then the derivative of w is equal to u prime of t plus I v prime of t, provided u prime and v prime exists. We have this example here, which I will go through the video, and the example I'll go through in this overview is derivative of an exponent. So we have derivative with respect to t, e z naught of t. So since we're not taking the derivative with respect to z, z naught now is considered a constant. It's just a complex number. So much like we would expect, just like for real numbers, we take our constant, we pull it out as a multiplier, and then we have e to the z naught t. But we can derive this formula here by using the strategy of separating our complex valued function into a real portion and an imaginary portion. So here we have e to the z naught t. I expand my z naught into the real and imaginary portion so that my exponent then can become a real portion and an imaginary portion. This portion here actually by Euler's identity expands to a real cosine y naught times t plus an imaginary portion I sine y naught times t. So from here, u is the real portion of my function is e x naught of t times cosine y naught of t, and my v is my e x naught of t no I in the v, sine y naught of t. And now I can take the derivative of u prime and v prime. So here's u prime, v prime, and then the rest is just taking derivatives and algebra. So various other rules such as differentiating sums and products apply just as they do for real valued functions of t. However, not every rule carries over to functions of complex variables. And an example of this would be the mean value theorem, which we will go over in this video. To take the integral of a complex valued function of a real variable t, so again, if w is equal to u of t plus I v of t, then the integral, we can take the real part separate from the imaginary part. So the integral of w of t is equal to the integral of u of t plus I integral of v of t. So for example, if we have the integral 0 to 1 of 1 plus I t squared dt, so again, this is a function that has complex values, but t here is considered a real number. So we start by squaring what we have inside, the 1 plus it. So we're going to get 1, and then here we're going to have it times it, so that'll give us minus t squared, and then we're going to have 2it, so that's I times 2t. So now we have a real portion and an imaginary portion. This is u and this is v. So we can take the integral from 0 to 1, 1 minus t squared dt plus I integral 0 to 1, 2t dt. And if you integrate this out, you'll see you get 2/3 plus I. You will see the anticipated rules for integrating a complex constant times a function wt, which is similar to what we have over here, which we did not go over, but we will in the video. And rules for integrating sums of such functions and for interchanging limits of integration are all valid, and moreover, the fundamental theorem of calculus can be extended. So we will see, and this is an example of using the fundamental theorem of calculus that we will do in this video. We will start again by looking what it means to be a complex valued function of a real variable t. So here I have wt is equal to u of t plus I v of t, where t is a real number. We say wt, this is a complex valued function because its output is a complex number. It's something with an I, a real part and an imaginary part. So we also think of w as taking a real number t and mapping it to a complex number. So these are the functions that we're talking about in this video. And what our first statement says about the derivative is once we have w is equal to u of t plus I v of t, then to take the derivative of wt, that's equal to u prime of t plus I v prime of t. So in other words, we can take the derivative of the real portion and then the derivative of the imaginary portion multiplied by I, and then add the two together. We will next use this result of taking the derivative for this example, which is to find the derivative of a complex valued function multiplied by a complex number. So we'll start with a complex number, z naught, which is equal to x naught plus I y naught, and we will take the derivative of this complex number times a complex function. So again, we're going to use our formula for taking the derivative of a complex valued function to derive a formula for the derivative of a complex valued function, that's our w of t, multiplied by the complex number z naught. And so I start by substituting z naught with x naught plus I y naught, and then instead of d dt, I'm just going to denote my derivative with the prime. The next thing I'm going to do, I can see that this x naught is just a real number. This u is a function, and actually the v is also a function, but we know how to multiply a real number or a constant times a function, so I'm going to do that. So I have x naught times u, and then I'm going to have here these two i's give me a negative. I'm going to have y naught times v, and then I'm going to have I times y naught times u, and then I times x naught times v. And again, here x naught and y naught are real numbers, and u and v are functions, but we know how to multiply a function by a constant. And now I can use my statement here that I can take the derivative of my real part and take the derivative of my imaginary part. So here, this is sort of like my new u prime, and this is like my new, I shouldn't say prime because that looks like derivative, right? This is like my u2, and this is my v2. And notice that both this u2 here is a real valued function because u and v are real valued functions. So this is a real valued function, and over here u and v are real valued functions multiplied by real numbers. So what's inside the parentheses, and what's inside both parentheses, are real valued functions. And since they're real functions now, I know how to take the derivative of them, and I know what happens when you multiply a constant times a real function and you take the derivative. The constant can just be pulled out, so I'll have the constant x naught times u prime minus y times v prime plus I y naught times u prime and x naught times v prime. And just to emphasize again, our problem here, what we're trying to do is to take the derivative or find a formula for the derivative of a complex valued function multiplied by a complex number. Here we have a real valued function u and v multiplied by a real number. So being able to do this here is different than what we're trying to prove here, but this is one of the steps we need to use. Now I can group my x naught plus I y naught together, and I can multiply u prime plus I v prime. You can see that you can verify this is equivalent to the expression above. So now this is z naught times w prime of t, which means this result, this derivative of this complex valued function wt multiplied by a complex number, is totally analogous to the derivative of a real valued function multiplied by a constant. Essentially, you just multiply the constant times the derivative. Here is the result we just went through, which was the derivative of a complex valued function multiplied by a complex number. And next, we're going to use this same formula here to derive the formula for the derivative of an exponent. And we will find the derivative of e to the z naught t is equal to z naught e to the z naught t. Very analogous again to real valued functions. And here I've made some space so we can go through the derivative of e to the z naught t. So here I've started by writing e z naught t. I've written z as x naught plus I y naught. So I have e x naught plus I y naught t. And then using my properties of exponents, I have e x naught t, e I y naught t. And then using Euler's identity, this is e x naught t. This almost looks like xot, but it's x naught t cosine y naught t plus I sine y naught of t. And remember, my u of t now is the real portion, which is x naught of t cosine y naught of t. And my v of t is the imaginary, what gets multiplied by I, which is e x naught of t sine y naught of t. And also, I know it's written here, but I'm just going to, for emphasis, I'm going to emphasize the fact that now u is a function of t. So remember, it's a function of a real variable t. It's not a complex number. In the previous videos, we had u of x, y, because, well, actually x and y were also real numbers. But now we're just talking about a single variable, real variable t. This next step then, the derivative of e z naught of t, by this statement here, I can take u prime of t. So u prime is, u is e x naught t cosine y naught t. So I'm going to take the derivative of that plus I times v prime of t, and v of t is equal to e x naught of t sine of y naught of t. So I'll take the derivative, I'll multiply I times the derivative of e x naught t sine y naught of t. So taking the derivative of this, making sure I use the product rule because I have two functions of t. So here I have the derivative of e x naught of t is x naught e x naught of t times cosine y naught t. And then I'm going to take e x naught of t times the derivative of cosine y naught of t. So that gives me a minus sign and a y naught sine y naught of t plus I. Now I take the derivative of this, again using the product rule. And so I have the derivative of e x naught of t, which is x naught e x naught of t times sine y naught of t minus, and now I have e x naught of t times the derivative of sine y naught of t. So I get my minus, I get my minus, and I'll have my y naught and my cosine y naught of t. From here, I'm going to take a quick look and see what result would be really nice. So if I know the derivative of e to the z naught t, it'd be really nice if the derivative was just z naught, bring down the, the derivative of z naught t, and then multiply by e z naught t. So what I'm going to do is I'm going to factor out my z naught from this expression. And when I do that, well, my z naught is now going to be in the form of x naught plus I y naught. And I see I can factor this out to e x naught cosine y naught t plus I e x naught t sine y naught of t. And you can multiply it out, but you'll see that this is exactly what this expression is over here above. But as I mentioned, this is super convenient because this is z. Now over here, I need to get it looking more like e to the z naught t. And I can do that by noticing my cosine y naught t and my I sine y naught t is equal to e to the I y naught t. So I factor out my e x naught of t, and then what I'm left with by using Euler's identity is e I y naught t. So I have exactly what I wanted, which is z naught e, and then this you see is equal to e to the z naught t. And I'm done with this derivation of this exponent derivative formula. Now it might seem these two examples were a lot of work just to prove what we would have done intuitively, and there are many rules which fortunately are just what you would expect. So differentiating sums and products, they apply just as they do for real valued functions of t. However, not every rule carries over, which is why it was important to derive them. So anyway, an example of something that doesn't carry over is the mean value theorem. So that's what we'll look up next. What the mean value says is that let Wt be a continuous complex function. In other words, and remember, we're going to evaluate this for the complex valued functions. We know it is true for real valued functions. We're going to see that this is not true. But let Wt be a continuous complex value function of t defined on the interval between a and b. By the mean value theorem, we expect, so again, it ends up, it's not true, but we expect there is a complex number c on the interval between a and b such that the derivative of w at c equals wb minus wa divided by b minus a. In other words, the average value of w on the interval b minus a. I am going to show you what this mean value theorem looks like on the real, when we're looking with real valued functions, when we're dealing with real valued functions. And the reason why I'm not going to show it to you on the complex valued function is because I really can't graph this well. So in particular, I can graph it for the real numbers because for real numbers, I only need one axis to represent a real number, right? So if I want to represent the number 2, I only need to put that on the x-axis. I don't need two axes. Unlike the complex numbers, if I want to show you a complex number, I need a real coordinate, which is on the x, and the coordinate for the imaginary portion, which is on the y. So in other words, for real valued functions, I can put the domain on my x-axis and I can put my range on the y-axis, and therefore I can graph f of x gives you y on a single plane. Whereas in the imaginary numbers, my domain needs an entire plane. It needs the xy plane. And then my range is the uv plane. And then we have this kind of mapping sort of picture. So it's harder to get a picture of the mean value theorem over here with complex valued functions. So I'm going to show it to you with the real valued functions. That was kind of a long explanation, and if I had just shown you this, you probably would have just been, but I felt like it was important to tell you and for you to think about. Okay, so the mean value theorem, what that is saying is here you have an interval from a to b, you have some function, this curve here, and you can draw, this slope between a and b for f of b minus f of a over b minus a. And the slope also represents that average value of w on the interval a and b. And what the mean value theorem says is in this interval, there's going to be some number c where the derivative of f at c is equal to this average value. And if I'm not sure I picked out the correct c. I'm not sure the slope is exactly equal, but let's pretend. This slope then is equal to this slope. And that's what the mean value says. You can find some number in the interval such that its derivative is equal to the average value along the whole interval. Average value of w on the interval. There is something else I should say about, because we're going to be talking about integrals soon, is that for real valued function, the integral can be interpreted as the area under the curve. That is not true for our complex valued functions for a couple of reasons, which we will see as we look more into integrating complex functions. Now, to show the mean value theorem does not hold for complex value functions, we're going to use a counterexample. So again, to show this is not valid for complex valued functions, we're going to use the counterexample, and we're going to consider Wt is equal to e to the it on the interval t between 0 and 2 pi. And we'll show that this mean value theorem does not hold. If we look at the derivative of Wt equals e to the it, what we get is I e to the it. This was something we had covered, an example we covered earlier on. And so if we look at the magnitude or the modulus of the derivative of Wt, we see that the radius is equal to I, which is equal to 1, which means that W prime of t is never equal to 0, because it always has modulus equal to 1. However, if we look at t going between 0 and 2 pi, we note that w of 2 pi is equal to w of 0. It's just equal to 1, both of them. So if t goes between 0 and 2 pi, w of 2 pi minus w of 0 is equal to 0. So these two sides of the equation cannot be equal. So again, w prime of t, which can't be equal to 0, is not equal to w 2 pi minus w of 0 over 2 pi minus 0 because this portion equals 0. So the mean value theorem does not hold. I'm also going to note that originally I was going to do this proof using this statement here, that this mean value theorem statement is equivalent to this integral statement. Since I didn't use it, I'm not going to go through this, but this is here for you if you ever want to use it. Now we are ready to cover definite integrals of complex valued functions of a real variable. And much like derivatives, if you have a complex function that you can separate out into u, a real function plus another real function v times I, then the integral of your complex function is equal to the integral of your real function u plus I times the other real function v. So now we're just integrating two real functions, which we know how to do. A quick example is the integral from 0 to 1 plus it squared dt. Because I want to get my function into this form of u of t plus I v of t, so two real functions, then I go ahead and expand this out. So you can see I have 1 plus it times 1 plus it. That's going to give me my 1. My it times it gives me negative t squared, and then 1 times it and it times 1 gives me I 2t. And now I can break it apart into 1 minus t squared. This is my real portion, and then my v is my 2t, which gets multiplied by I. And from there, it's regular integration in algebra, and my solution is 2/3 plus I. That's an I, not a 1. So this is quite nice, again, because what this does, when you have real variables t, what that does is allow us to break this function into integrals of two real valued functions, which we know how to do. Also, anticipated rules for integrating a complex constant times a function, we'll do an example of this, is what you would expect. Rules for integrating sums of such functions and interchanging limits of integration, they are all valid. We will also see that the fundamental theorem of calculus can be extended to the complex valued functions with real variables. Our first example uses the derivative of a complex constant times a function wt, and I'll remind you, we had done this example earlier. The derivative of e to the it over I, we could pull out the complex constant, which is 1 over I, and then take the derivative of e to the t, which is just I e to the t, and then we got e to the it. Using this, now if we want to integrate from 0 to pi over 4 e to the it, that's just going to equal to 1 over I e to the it evaluated at 0 and 4. I plug in my values, e to the I pi over 4, and then minus 1. I would actually stop here, but if for some reason you need to show it is equal to this value here, or if you just happen to see that you can then apply Euler's identity to this e to the I pi over 4, you would get 1 over I cosine of pi over 4 plus I sine pi over 4 minus this 1. And then you would evaluate your sines and cosines algebraically until you get 1 over square root of 2 plus I, 1 minus square root of 2. The rule that we use, and probably one of the most important ones we want to use, is the fundamental theorem of calculus. And in fact, in our last example, we used the fundamental theorem of calculus when we plugged these numbers in over here, and we used it almost without thinking. But it's time to take a closer look at the fundamental theorem of calculus. Looking at the fundamental theorem, first I'm going to remind you the fundamental theorem for real valued functions that you learned in first year calculus. And that said the integral from a to b little f of x dx is equal to capital F of b minus capital F of a, where capital F is the antiderivative of little f. In other words, capital F prime of x is equal to little f of x. And of course you use this all the time. The reason why this is called the fundamental theorem of calculus is, well, first you use it all the time and it's super useful, but the thing that's so fundamental about it is it relates our integrals with our derivatives. Analogously, what we want to show is for complex valued function, the integral from a to b of wt dt is equal to capital WB minus capital W of a, where wt is composed of ut plus I vt, and capital U of t is equal to the antiderivative of u of t, and capital V of t is the antiderivative of v of t, and capital W of t is equal to capital U of t plus I v of t. We start with the integral from a to b of wt dt, and by our definition over here, or our fact here, we can break that into the integral of u of t dt plus I integral of v of t dt. And now we have u of t and v of t. These are just real valued functions, so we can just take the antiderivative. We can use this fundamental theorem of calculus for real valued functions, and this would be evaluated at the antiderivative of u of t, evaluated at b and a, and the antiderivative of v of t evaluated at b and a, which is then equal to capital U of b minus capital U of a minus I capital V of b plus I capital V of a. So I kind of rearranged the term, but these two come from our u of t, and these two come from our v of t. This here is capital W of b, and this part here is capital W of a. So we have what we want to prove. Although I did actually write one extra step, W of b minus W of a, that's W of t evaluated at b and a, which is WB minus WA. So we have proven the fundamental theorem of calculus for complex valued functions of real variables t. I want to point out that a lot of these, the derivative and the indefinite integral, separated out nicely, and also the fundamental theorem of calculus holds as long as they're real variables, and that's one of the crucial things we have to realize is that for the fundamental theorem of calculus, we were dealing with real variables. And the reason why that's important is here I also did real value functions, real variables, but the idea is sort of the same for complex functions, real variables, is that when we integrate from a to b, so as long as our variable is real, it's very clear what we're integrating. We're integrating along this path from x, the real number a, and we keep increasing until we get to the real number b. There's only one path, this straight line from a to b. However, now in contrast, when we're talking about complex variables, when you integrate from a complex number a, it's equal to x1, y1, and you integrate to a complex variable b from x2, y2, there's several paths I could take. So you could take the straight line and integrate along this path, or you can take a circular path, or you could take, let me do this in a different color, or you could take a curvy path. You can take all kinds of paths. You can take really strange paths. So at this point, when you're dealing with complex variables, now you're going to integrate from a to b f of z. Now z is a complex variable, dz. You get more variation where the fundamental theorem of calculus will not hold because your integral will be dependent on the path. But we'll be looking at that more in the next couple of videos. And by the way, so these integrals are going to be contour integrals, path integrals, like you did in vector calculus. And this preview is kind of one to get you thinking about how functions of complex variables are different than when you have real variables, but also so that you know that the familiarity of the things we've done in this video, that you shouldn't take them for granted. To review what we've looked at in this video, we looked at the derivative of complex valued functions of a real variable t. And what we saw is if our function that we're taking the derivative of, we can separate it into a real portion and an imaginary portion. This v is a real function that we multiplied by I to give us the complex function. Then the derivative of w of t is equal to the derivative of u of t plus I derivative of v of t. We did an example where we computed the derivative of a complex valued function multiplied by a complex number. So we assumed w was a complex function, and we multiplied by a complex number, and we wanted to take the derivative. We expanded our complex number into an x naught plus I y naught, and this will allow us, because now our x and our y's and our u's and v's, our u is a real valued function, and our v is a real valued function, so we can multiply. We know how to multiply a constant times a real valued function, so we can multiply this out. This is x naught times the real valued function u, and then we have our minus I, that becomes -1, and then our y naught is a constant value times our real valued function v, and then we have I times x naught times v, and I times y naught times u. And then we still need to take the derivative. And here is where we use our equation here, where we can take the derivative of the real part plus I times the derivative of the imaginary part. So I have the derivative of the real part plus I times the derivative of the imaginary part. And note here, I have this whole thing, y naught u plus x naught v, as like my new v2, like my new imaginary part, because that's what's multiplied by I. So take the derivative separately. I know how to take the derivative of a real number, real valued function minus a real number, real valued function. I can just take the constant out. So x naught u prime plus y naught v prime. Similarly here, I have I y u prime plus x naught v prime. I rearrange, I factor out my x naught plus I y naught 0, because it would be really convenient if this looked like z naught and w prime of t. And when I factor out a z naught, this part, what I'm left with, is w prime of t, which is very convenient because we have this nice formula where the derivative of a complex number times our function is equal to the complex number. We just pull out the complex number as a constant times the derivative of wt. We did this other numeric example here, and we noted there are many rules, such as differentiating sums and products, that they apply just as they do for real valued functions. However, we also saw that not all rules carry over to functions of complex variables, and our example that we showed was the mean value theorem. We continued with definite integrals of complex valued functions of a real variable t, and we said if w of t is equal to u of t plus I v of t, then the integral of wt dt is equal to the integral of u of t plus I integral of v of t. And we have this example here. So if we have the integral from 0 to 1, 1 plus I t squared, when we square 1 plus it, we get 1 minus t squared plus I 2t. By our formula here then, this is the integral of, our formula here, I'm sorry. This will then be the integral of u of t, which is 1 minus t squared, or the real part, plus I times the integral of the imaginary part, which is 2t dt. When we do the integral and the plug in the final numbers, we get this is equal to 2/3 plus I. We also found there are many rules: integrating complex constant times a function wt, integrating sums of such functions, and for interchanging limits of integration are also valid, and moreover, and importantly, the fundamental theorem of calculus is also valid. And we did the proof to show that we can have the fundamental theorem of calculus be extended to complex valued functions with real variables, and we also did some other commentary about basically just complex valued functions. We also had this last example here. We used the fact that derivative, which we got from up here, we used this formula, the derivative of e to the it over I is equal to 1 over I, just pulling out the constant 1 over I, derivative of e to the it, which is equal to e to the it. So we use that in our integral 0 to pi over 4 e to the it dt. Then the antiderivative is 1 over I, e to the it, 0 to 4. So we used our fundamental theorem of calculus. We plugged in pi over 4 for t minus 0 for t, and then we simplified this and did some calculations until we got 1 over square root of 2 plus I times 1 minus 1 over square root of 2. At this point, I have 2 problems for you to try, so I suggest you pause the video, give them a try, and then come back and I'll have solutions for you. Here are the two solutions to the two problems. And that's it for this video. Thank you for watching.